Hello and welcome to another Andy's Workshop video. In this video we're going to take a look at this GPS Disciplined Oscillator, or GPSDO as they're shortened to. I got this one on eBay a while ago because I needed to calibrate a frequency counter that I built. You can see the details of that particular project also here on YouTube and in my blog. It worked very well for that task, and now we're going to do a detailed review of this oscillator. You'll see it in action, and then afterwards I'll tear it down and we'll see what's inside. Because this particular one was advertised on eBay as being Symmetricom inside. Now Symmetricom were, should I say, because they're now being bought by Microsemi, they were well known in this field, so it'll be interesting to see just what type of Symmetricom parts we've got in this device. Now as far as accessories go, you don't get much with this box. You just get an external 6-volt wall wart type power supply, and you get one of these disc antennas, which you just need to place somewhere where you have in your room where you have a very good view of the sky. I use a windowsill, and luckily it comes with 10 meters of cable here, which is good because the window that I need to use isn't directly next to my desk. It's several meters away, so I was happy to see that it came with such an enormous amount of cable. So without further ado, let's get this thing powered up, and we'll see what it's like in action. Alright, so the oscillator has now been switched on for about an hour and a half, and the little lock light has started flashing at a steady rate. When you first switch it on, the lock light goes solid, and I believe during that period the device is sampling from the GPS and doing its averaging and basically waiting until it's got enough samples to decide that it's got a frequency worth outputting on the 10 megahertz output here. So what I've done is I've connected up that 10 meg output to my cheapo Chinese oscilloscope, the 01 DS7102V. It's one that many people I know have bought, so I thought I'd just use this one. Let's switch it on and see what the GPS is outputting. I've hooked it up to channel 2 here because channel 2 is it's coloured yellow and it's more visible on these videos. Channel 1's red and it's quite dark. And there we go. That's a nice stable signal. Let's have a play around. Yeah, as expected, it has started outputting a nice solid 10 meg. Let's add on frequency measurement for channel 2 just to see what the oscilloscope thinks it is. If I can remember how to do it on here, so it's going to be measure, we want to do add, source channel 2, type, let's move that down up to frequency, let's do that, and it's decided it wants to put it back to channel 1, that's silly, add, and there we go, down the bottom. I don't know whether you can read that, let's see if I can get better focus. It's measuring the frequency, and a digital sampling oscilloscope is not the best thing for measuring an accurate frequency, but it's showing here, yeah, 10.00 megahertz, which is what we expect. So it does work. Now let's hook it up to my frequency counter and we'll see what it looks like there as well. Okay, so what I've done here is I've connected up the GPSDO to my nano counter, frequency counter. This is a project I built a while ago, probably more than a year ago now actually. But if you look on the on the rest of my channels, you can see the video that I made describing how this thing works, how I built it, etc. So I won't go into detail now. Suffice to say that it uses an FPGA to do the counting, to do accurate counting, and it has a nice onboard temperature-controlled oscillator to do as a frequency reference. Of course, that frequency reference is nowhere near as good as the GPSDO that we're looking at today. And I've got the GPSDO feeding into the sample input. So what we're seeing as a measurement here is that the onboard oscillator is off by 4 Hertz. You would normally, in normal operation, you would you'd use a GPSDO as the reference clock itself, and to do that you connect it up to the external ref here. But with it connected to the sample input, we are using the onboard Connor-Winfield temperature-controlled oscillator to do the counting, and we're treating the GPSDO as a sample. So we actually know the GPSDO is bang on 10 megahertz. So what we're seeing is the error of the Connor-Winfield TC-XO on this board itself. So what I could do here, what I can do in my software, is take a calibration value. I can say that the input is 10 meg exactly, and I can create a calibration value of 4 Hertz to calibrate this counter. And from then on, I know that for a reasonable time going forward, this counter will be accurate. But as expected, during this entire clip, the frequency input has not changed one bit. and I'm not surprised. The temperature in this room is stable, so the TCXO isn't expected to drift, and the oscillator, the GPSDO, is of course perfectly stable itself. So I know we haven't learned a great deal here, but it's nice to just show the the frequency coming in is completely stable, and it's as expected. It is. Okay, so we've learned a bit about the theory of how GPS disciplined oscillators work. We've connected this one up, we've seen it locked to the GPS satellites, we've seen the shape of the waveform that comes out of it. We've done some experiments to measure the frequency. I think that's all we can do from outside, and now I think we should take this thing apart, see how it's built, look at the components, that the choices that have been made, and see if it's generally put together as we've been expecting. So without further ado, I'm going to get my screwdriver out and let's take this thing apart. Okay, so this thing's constructed from basically just a piece of extruded aluminium that holds the board itself. The front plate is made from a PCB with some holes drilled in it to accommodate the BNC connectors, and another hole for the DB9 connector there and the LEDs. And it's quite a cost-effective way of making a front panel, this, because prototype PCBs are so cheap these days. It's held in by 4 hex screws. And on the back we've just got looks like an aluminium plate with some ordinary Phillips screws here. So I should be able to take this apart with just a simple screwdriver. Let's have a start on it. Okay, let's get these out to begin with. That's 1. 2. 3, and that one doesn't look like it was put in properly. That's a bit stiff. Let's get that out. Okay, no worries. Right, let's move those screws out of the way. Don't lose them. Let's ease the back off and see what we've got inside here. Oh, okay. Yeah, that's more or less what I expected. I was expecting 2 boards. Yeah, interesting. Okay, so I'm going to have to... Yeah, okay, so I'll have to take off the antenna connector from the back here, and then I can undo the front and slide the unit out that way. Alright, so I'll just pause while I go and find a spanner that will fit that antenna connector. Okay, so an appropriate 8mm spanner has been found, so let's continue with disassembling this thing. That's enough to release it. Take this nut off. Extract that, put those to the side. And now I can take the front panel off. Right, here we go. Already prepared the appropriate hex driver for this. Apart. Looks like I'm going to have to remove the BNC wash. Oh no, I won't. I can just take the whole thing out. Oh, that slides out nice and easy. No problems there. Ooh, look at that. That's nice, isn't it? Okay. Oh, interesting. Oh, there's more circuitry on there than I expected to see. Cool. That's upside down. Let's get the silk screen the right way up. I think we're going to have to go to a macro lens to investigate this any further. Okay, so we're back in a second. Alright, so if I were to summarise how this board has been constructed, it's basically a pull from an existing unit. This main circuit board here is by a company called Symmetricon, which are quite well known in the GPS disciplined oscillator industry. What's happened is this board must have come on sale. It'll have been taken from a piece of decommissioned equipment, possibly a cell base tower, something like that. And it's been picked up by somebody in China, and they've built a board around this. So it's basically, they've mounted it on their own little circuit board here, and they've put on another circuit board to form the front panel on this side here. The only thing holding the front panel on is the screws on the nuts on the front of the BNC connectors here. Now I can tell obviously that quite a bit of the functionality of this original board is not used in this oscillator implementation, because there's a great big ribbon connector here. You know, that's for a flat flex cable, and there's nothing going into it. It's unused in this particular implementation. So let's have a look at the key components on board this thing. Okay, so the main GPS unit is here. It's by a company called Furuno of Japan. The antenna comes in right next to the GPS unit. All the processing will go on inside this entire module, this RF module here. And then here is the ovenized oscillator. It's by Symmetricom themselves. I googled around for the part number. It says STP2695. I can't find any data sheet on this, so no luck there, unfortunately. What I was hoping to do was figure out how much this drifts per year and how much it can be adjusted by the control voltage, because there's a date code here and it says 1205, so that'll be the 12th week of 2005, making this particular oscillator units 11 years old at this point in time. Now, over 11 years, even the best oscillators drift. And I'd like to know how far this one could have drifted over 11 years, and whether the control voltage is allowed to correct the frequency back into range after a potential 11 years of drift. If it can't, then this unit could possibly be out of spec, and I reckon these units, these boards, are decommissioned from cell towers or wherever they've been used in over a sort of a fixed period, like 10 years perhaps, because the ovenized oscillators in them could have drifted so far out of spec that they could no longer be corrected. Obviously, if I can't find a data sheet on that STP 2695, then I'll never know whether it's capable of being in spec at this particular age. But yes, I'll just have to look out for it in the future. The other board attached to it here is this here. This is a boost converter. I had no idea really why it's on a separate board. That's a boost converter, and that little chip you can see in there says 7806 on it. And a 7806 is a linear regulator, so it's possibly a boost module followed by a linear regulator to smooth out the kind of noise that you get from a boost converter before sending the the power supply into the main board. And it may be on a separate board here just to reduce noise. I'm not sure, but that's the only reason I can think of. Other than it's easy replacement by just taking these screws out, I can't think of any reason why it would be on a separate board. Now, if we look at how the module's connected in to this base board here, which is this is the amateur section. If you think of that as the amateur section, and this is the professional section. It's connected in by they've just soldered. There used to be an SMA connector here. You can tell. I'm going to actually wait a second, and I'll zoom in on this because you can't really see at this resolution. There we go. That's better. Now you can see the footprint here. You can see what they've done. Now I recognise this pattern here, this footprint, as being from a mini SMA connector that's would be used to attach a proper RF cable to this board. What they've done, I think, is they've just desoldered the SMA connector, and they've just patched in this lead here. It is an insulated, shielded lead. It does have a ground shielding going around the outside of it. You can see they've just stripped it back to expose the ground shielding there and soldered it on to the ground pad here, and the signal connector goes into the centre. Now that's a bit it's a bit shonky really, but I guess it works. And then the signal goes out to the board here, and then across a single trace out to the BNC connector, surrounded by a ground fill here. Plenty of grounding on the bottom there, no problem with that. Now if we move across to some more of the control parts here, these are the outputs. This is really not very good construction, to be honest. The soldering ain't that bad. I've had a look at the actual solder joints. They're not dry or anything like that, but they just haven't bothered to clean, so there's flux everywhere. And these are the thinnest cables I've ever seen in my life. They just connect up the LEDs, so no real worries with that. So these signals just go across the board to the LED stack at the front here. The LEDs are little vertical mounts. Right, let's move over to the 1 PPS output, which is just there in the corner, just there. And I've done a similar trick by removing what I think is the mini SMA SMD connector, and they've just soldered in wire that needs to go out to the board here and then through a trace to the 1 pps output. Again, it's a bit, how you're doing, but I guess it works. You certainly wouldn't see that kind of job in a professional product though. I'll just finish up here with a quick close-up of that regulator board again so you can get a good look at it. Currently the little boost module's in focus there. Let's just focus on the main board itself so you can see the rest of it. It clearly is a regulator board. That's let's get the pointer. That's the boost converter. That there is, I suspect it's a FET of some kind. There's the diode, the main diode. Output capacitor, input capacitor, and I suspect that is current feedback. It looks like it's a 1 ohm resistor, so it looks like it's some kind of feedback resistor for the boost module. Right, I'm going to put it back together now. Now I've seen what's inside it. To be honest, I was expecting different. I was expecting to see a homebrew device made out of the overnight oscillator, the GPS, and perhaps a microcontroller with some homebrew firmware. But instead, I found an entire GPSDO ripped from something else. It's quite a surprise. I'll just have a quick poke around, see if I can see anything dodgy around the DB9 connector and the associated connections back into the board, because as I mentioned earlier, I can't get a signal out of this COM port. If I can find something looking dodgy, then hopefully I can fix it while I'm here. But I think now after that I'll put the case back on it. Okay, it's all safely back in its case now, and I think with that I'll conclude this video. I've shown you this oscillator in action. I've taken it apart and given you a look at the insides. It was certainly a surprise for me. I haven't actually taken this thing apart before. That was the first time I've seen inside it. It did reveal a few surprises, and the only thing that's outstanding for me really is why I can't get this RS-232 port to work. Maybe it needs a null modem cable instead of a standard serial port. I'll have to investigate the pinouts and see if I can make it work, because I did buzz out the connections inside, and the continuity between the pins here, the DB9, and the board inside, it's all fine. So there's no real reason why it shouldn't work unless one of the ICs on the board has failed. But I will continue to investigate that, and if I manage to get it to work, then I'll post it on my blog. Okay, so I think we're all done. Thank you very much for watching, and I hope you've enjoyed it.